Hello. So in the last video, we started to show ways of arguing that the language is not regular. So showing limits on what finite automata can do. And we did it through the pumping lemma. In this video, we are going to see something that you can do with finite automata, and this is to minimize a finite automata. And the two are related. The fact that finite automata are limited is what's allow us to do various remarkable things like minimize and optimize a DFA. And the techniques that we will use here will actually be useful towards the next video, where we will show the mile-narrowed theorem that gives us another way of arguing that a language is not regular, and that way would actually be a characterization. So that the pumping lemma may or may not allow us to argue for any given non-regular language that it is non-regular, but the mile-narrowed theorem gives an if and only if condition. So every language that is not regular, we can argue that it's not regular through the mile-narrowed theorem. Nevertheless, we were going to start with this positive aspect of the limitation of finite automata, which is that we can optimize them. So let's look at this example and ask, is this DFA as the minimal number of states? So let me ask it more formally. Can we accept the same language as this DFA with another DFA that has less states? So you can stare at this, and if you stare long enough, you can see that, in fact, we can associate the two accepting states and the two rejecting states, each one of them into a single state that is marked by yellow. And it will turn out that we get the same language. So the new DFA operates in exactly the same way. In fact, and we will formalize all of that later on, we can argue that the states that we are combining are indistinguishable from one another. They have the same operation. And that's the reason that we can combine them and minimize and get this DFA that does the same thing. So is this DFA minimal? You can pause and think about it. Well, this DFA is minimal, and we can argue that by noticing that this DFA has words that are in the language and words that are not in the language. It accepts some words and rejects some other words. And to be able to reject and accept some of the words, you need to have an accept state and a reject state. So 2 states is really the minimal number of states we can have, unless the language that we are recognizing is either the complete language or the empty language. But this is a very, very limited case in which we can argue minimality. The question is how to do it more generally. How can we tell in general whether a DFA is minimal? And furthermore, if it's not minimal, how can we come up with another DFA that is minimal? So the theorem that we're going to prove during this video is that for every regular language L, there is a unique up to relabeling of the states, minimal state DFA M star, such that L of M star is exactly L. And furthermore, there is an efficient algorithm which, given any DFA M, will produce a unique M star such that L of M equals L of M star. So let me stay a little with this notion that the minimal state DFA is unique. And you see that it's unique up to relabeling of the states, renaming. And the point is that every DFA can be changed to another DFA that does the same thing by just renaming states. So now this state was called Q2, and this state is called Q3. We can instead call the other state Q2 and the other state Q3. So switch the names. And this will look like a different DFA, but inherently it is the same DFA. Up to naming, it is the same DFA. And so we're going to argue that the minimal DFA is unique up to renaming, and that we have an efficient algorithm that does that. And if such optimization was true for more sophisticated models of computation, it will be an amazing engineering breakthrough. So imagine you take a mediocre software engineer to program something in C++ or some other language. And now automatically you're able to optimize the program that was written for one of any optimization goals. For example, making the code better, nicer, shorter, or making the algorithm more efficient. That would be amazing, and we don't expect it to be true in general. But for DFAs, we are able to do that. That's one reason that the DFAs, finite automata, are so useful in areas like verification that tries to automatically verify correctness. The ability to do such optimizations with DFAs is very useful in this context. And as a note, we want to point out that there isn't a uniquely minimal NFA. So these two non-deterministic finite automata accept the same language. So what's the language? This is the language that contains strings that have at least a single zero and are completely composed out of zeros. So every number of zeros larger than 1. And both of them recognize the same language. So there isn't a uniquely minimal NFA. This is an interesting property of DFAs. And we'll work our way to prove this theorem. This is going to be one of the longest videos that we're going to record. There's a lot to define, a lot to prove, but the end result is really nice. So it's nice that we can optimize DFAs. I hope, and I'm quite doubtful that by the end I won't be able to confuse myself, but hopefully I'll do a good job. And indeed, it's not ideal, the format where this is a recorded video, but potentially by rewinding the video, you can do better in terms of understanding the proof. And I will also release notes for this proof. So let's start with a few notations. And here we want to extend the transition function delta to strings. So given a DFA M, which has a transition function small delta, we're going to define an extended transition function big delta that takes a current state and a string and transfer to a new state. And this state is the one that you get by reading the string in your input. And the extension will be pretty obvious. So if we look at delta of Q and epsilon, the empty string, you just stay put, right? When you start at the state Q and you read the empty string, you stay at Q. If you read a single symbol, so from Q, then you move to whatever the original transition function tells you to move. The original transition function is defined for a state and a single symbol. So here in the middle, we have just the original transition function. And now let's consider what happens when you look at a longer string. And this definition will be a recursive definition. So given a state Q, if you read the symbol sigma 1 up to sigma k plus 1, it is the state you reach from delta of Q sigma 1 up to sigma k when you notice sigma k plus 1. So recursively, this is defined to tell you which state you reach from Q when reading sigma 1 up to sigma k. And small delta, the transition function, small delta, will tell you where you reach, what's the state you reach when you also read sigma k plus 1. So that's going to be a useful definition, but what it does is pretty natural. So delta QW is the state of M reached after reading W starting from the state Q. With this notation, we have that delta of Q0W is an accept state if and only if M accepts W. Because delta of QW is an accept state means that when you read Q0 and when you read W from Q0, you reach an accept state. And this is exactly the definition of accepting the string W. And now we can define what we really wanted to define, and this is related to the example we had before, meaning that a string W distinguishes states Q1 and Q2 if when you start from Q1 and read W, you are an accept state, and if you start with Q2 and read W, you're not an accept state, you're a reject state. In particular, Q1 and Q2 cannot be the same state, and in fact, they have different functions. You cannot allow yourself to forget. If I tell you that you're in Q1 or Q2, you are not allowed to forget which one you are, because if the next string you're going to read is W, then you won't know if you're supposed to accept or reject. So W distinguishes the states Q1 and Q2. It shows that they are actually different and have a different function. Put differently, W distinguishes these states if exactly one of delta Q1 and W and delta Q2 and W is a final state, is an accept state. This definition can be interpreted as follows. So imagine that you have a finite automata, and it knows that it's either in Q1 or Q2 and doesn't know in which one it is. W allows you to tell if you're in Q1 or in Q2. So if you read W and you see if you're accepting or rejecting, you know which state it's going to be. The state that leads you to accept, for example. Now let's look at an automata M and two states P and Q. And we define that the state P is distinguishable from Q if there exists some W that distinguishes P from Q. There is some W such that delta PW and delta QW operate differently. One is accept and one is reject. And this would mean that these two states have a different function. You cannot merge them like we did in the example in the beginning. States P and Q are indistinguishable if they are not distinguishable. And this will mean that you can actually merge them like we did in the example. So pairs of indistinguishable states are redundant because if you're in P and you move to a different state, Q, which is indistinguishable, and now you continue reading the string, then you'll never reach the wrong conclusion. If you were supposed to accept, you're accepting. If you're supposed to reject, you're rejecting, regardless of what's the next bits that you're going to read. So let's look at this as an example for what states are distinguishable. So which states are distinguishable here? Well, one thing is that every final state, any accept state, is distinguishable from non-accept state, right? So for example, Q0 and Q1 are distinguishable because the empty string accept cause you to accept if you start from Q1 and cause you to reject if you start in Q0. So the kind of first thing we can observe is that an accept state and a reject state are always distinguishable from each other. So now we only need to ask ourselves whether Q1 is distinguishable from Q2 and Q0 is distinguishable from Q3. What about Q1 and Q2? Well, Q1 and Q2 are distinguishable because if you take a 0 from Q1, you reach Q2, which is accepting, but Q2 on a 0 reach Q3, which is rejecting. So the string 0 distinguishes Q1 and Q2. What about the string Q0 and Q3? Are they distinguishable? Yes, they are distinguishable. The string 10 distinguishes Q0 and Q3. If you take 10 from Q0, you reach Q2, which is accept. If you take 10 from Q3, you reach Q2 and Q3 back, which is reject. And one way of knowing that they are distinguishable is just to look at 1. 1 from Q0 reaches Q1, 1 from Q3 reaches Q2. We already argued before that Q1 and Q2 are distinguishable, and if by taking the same symbol or the same string, you reach two states that are distinguishable, you can conclude that the states you started with are distinguishable as well. And that's not hard to argue. You concatenate the string that got you to these two distinguishable states with the string that distinguished these states. So here you can concatenate 1 with 0. 0 is the one that distinguishes Q1 from Q2. And so 1, 0, which is the concatenation of these two strings, distinguishes Q0 from Q3. And we will use this fact later on in our algorithm. So which pairs of states are distinguishable? There's no two states are distinguishable. So here the string 0 distinguishes Q1 and Q2. And So we have this notion of indistinguishability, and this notion allows us to define a binary relation. Let's call it tilde, such that P is related to Q if and only if P is indistinguishable from Q. And this binary relation will have some good properties. So P is not equivalent to Q if P is distinguishable from Q. And I already gave the hint that this relation is an equivalence relation. An equivalence relation has three properties that makes it pretty similar to equality. So in some sense, these are two properties that equality has, and these will be useful for us. So the three properties of equivalence relation are: first, P is equivalent to P, it's reflexive. Then if P is equivalent to Q and Q is equivalent to P, then Q is equivalent to P. It's symmetric. And these two properties are very easy to argue for the relation we just defined. A state in itself are, of course, indistinguishable. Whatever you do from the same state reaches the same state. And the definition of distinguishable is symmetric, so definitely P is equivalent to Q means that Q is equivalent to P. And the third property is that it is transitive. It's a little bit harder to argue, but not much. So P is equivalent to Q and Q is equivalent to R, then P is equivalent to R. So what's the proof? You can view it either the positive or the counter positive. So let's say that P is not equivalent to R for the sake of contradiction. If they are not equivalent, then there is W that distinguishes P from R. And by the definition of what does it mean for W to distinguish P from R, we can see that either W distinguishes R from Q or it distinguishes Q from P. Because W from R and from P reaches two states, one of them is accept and one of them is reject. And no matter what happens from Q, it will let us distinguish one of these two pairs. So, so that's this notion of equivalence relation. And one nice thing that equivalence relations let us do is divide the partition, the set of states Q, into disjoint equivalent classes. So what does it mean? We look at all the states Q, and we within each one we divide it to we partition it such that within each region all the states are equivalent to each other. And the properties of an equivalence relation says that this is possible. Essentially, you can do this division by looking at any state and then looking at everything that is equivalent to this, and this is one group. And because of transitivity, all of the strings will be equivalent to each other. And you continue. So, given a finite automata, Q, we divided the states, we partitioned them to equivalence relations. We denote any equivalence relation as a Q in these brackets, which is all the states that are equivalent to Q. So you can name it for each one of the states here, and it will give it the same group, again, because of transitivity. And what we're going to do in our construction is take the automata, look at those equivalent classes, and just like we did in the example at the beginning, we are going to merge all the states in each equivalent relation. This will be a way to get a smaller finite automata that does the same thing. And we will argue that essentially there is one more thing we need to do. Just by this local operation, we get something that's minimal. So let's look at this example again. When we look at the equivalence classes, these are the equivalent classes. And now we can merge them into these two megastates and get our minimal state. That's exactly what we did in the beginning. So let's take it more slowly and show how to do it in general. So we want an algorithm that we'll call minimizDFA. And that algorithm is supposed to produce the minimal DFA that is equivalent to your input. So the input is a DFA M. The output is a DFA M min, which ideally is going to be the minimal DFA that is equivalent to M. But let's see what the properties that we're going to show. First, this is equivalent, so they both recognize the same language. L of M is equal to L of M min. M min has no inaccessible state. So I mentioned that there is one more action we need to do to minimize a DFA. And this is, we can immediately remove every state that we cannot reach from the start state. If you cannot reach a state from the start state, then there is no point. Removing it doesn't make any difference. So definitely the output of this algorithm, minimizDFA, cannot have inaccessible states, otherwise it's definitely not a minimal DFA. And finally, M min is irreducible. Irreducible means that there are no two states that can be merged. So more specifically, it's irreducible if for every two states that are in M min, P and Q, the two states are distinguishable. So these are these two properties that we're going to have. And the theorem that we're going to prove is that M min is the unique minimal DFA that is equivalent to M. And in fact, we'll conclude it from these properties. That it is accepting the same language, it has no inaccessible states, and it is irreducible. So interestingly, there are two simplest ways in which you can reduce the size of a DFA, and as it will turn out, just doing these two things, removing inaccessible states and then merging states that are equivalent to each other, will be sufficient. Okay, so let's work our way into proving this theorem. And so what's the intuition? The states of M min will be the equivalent classes of the states of M. We are essentially doing what I was saying we're going to do. We're going to merge every two states that are equivalent. This is the same as viewing the entire equivalent class as one state. And so if that's what we're going to do, we need to really understand which states are equivalent to each other. We need, the first step of our algorithm is to discover these equivalent classes. And we'll do it via a dynamic programming. So the first thing we're going to discuss is this dynamic programming algorithm. and the properties that it has. So we call this algorithm the table filling algorithm, which I think is a good name for most dynamic programming algorithms. The input is a DFA M, and the output is going to be a table, DM, that contains pairs PQ that are indistinguishable from each other. So we're going to have all the pairs that are indistinguishable from each other, and we're going to see it in a table. Once we have all the pairs that are distinguishable from each other, we also know which ones are indistinguishable from each other, and these indistinguishable states can be clustered into equivalent classes. So the other output is the equivalent classes of M, which is this family of sets. It's this partition. And this follows from the first thing we do. So here's the high-level idea. We're going to do this recursively in iterations. So the first thing we know is that pairs of states, one is accept and one is reject, are distinguishable by the empty string. So the first thing we are going to identify is all these obvious pairs. Pairs where one is accept and one is reject, these are obviously distinguishable. Then we're going to go in iterations, and in each iteration we will try to find states that are distinguishable by longer strings than we uncovered so far. So we'll have iterations, and in each iteration we'll try to find some other pair of distinguishable states. And once we cannot find anything else, then we will conclude that all other pairs are indistinguishable. That's kind of the very, very high level idea. Don't worry, we're going to see exactly the algorithm here. So we have a table that looks at the pairs Q0 and Qn. We don't need the entire table because we have symmetry. We know that if Qi is indistinguishable from Qj, then Qj is indistinguishable from Qi. So we only need half of this table. The base case is all PQ such that P is an accept state, Q is a reject state. So here we identify that Qi and Qj. Oh, sorry. Qi is if Qi is the accept state, then it is distinguishable from every other state. So in this case, we only had one accept state, and it is just distinguishable from all the rest. Then we go in iterations. In each iteration, we search all pairs of states that we didn't already determine that are distinguishable. So we look at every PQ like that we don't know what happens. There is nothing in this table. So we look at an entry in the table that is empty. And now we look at any possible symbol, sigma in the alphabet, and we're trying to see if sigma is going to give us evidence that P and Q are distinguishable. So what we're going to check is which state are you reaching from P on sigma, and which state are you reaching from Q on sigma. And now if these states are P prime and Q prime, and we know already from previous iterations that PQ and P prime and Q prime are distinguishable, we are going to conclude that P is distinguishable from Q. So again, if you have two states and with reading a symbol sigma, you reach two other states that are distinguishable, then just like we kind of sketched before, it means that P and Q are also distinguishable. So we repeat this until there are no more entries that can be filled, no more Ds that can be added. So we go in iterations. In each iteration, we go over all the empty squares. And for each square, we go over every alphabet symbol, and we see if something happens, if we identified another distinguishable pair. And if we go for an entire round without making any change, we can stop. So why can we stop? We definitely have no advantage in continuing because we just went through an entire iteration without making any change. If we'll do another iteration, nothing changed, so we will not find anything new. So definitely there is no point in continuing. What we'll need to argue is that the moment we stop, we actually uncovered all the pairs of states that are distinguishable. So let's look at this algorithm here. We have this table. The table needs to look at all the pairs. We have 6 pairs to care about. And what we first see is that Q3 is an accept state, which means, and it's only the only accept state, it means that it is distinguishable from all the rest. So these are the first Ds that we can do. Now we're going to look at a pair, Q1 and Q2, and ask ourselves, is this distinguishable? Can we find a simple evidence that it is distinguishable? So let's see. If you take the string 0 from if you read the symbol 0, it will not distinguish the two strings. They will actually reach Q2. But if you take the symbol 1, from Q2 you'll reach Q3, and from Q1 you'll reach Q0. Now Q0 and Q3 were already determined to be distinguishable. Therefore, we can also say that Q1 and Q2 are distinguishable. Let's continue forward. Let's look at Q0 and Q1. Q0 and Q1 are not distinguishable by the symbol 1. If you take 1, both of them will reach Q0. But if you take the symbol 0, you'll reach Q1 and Q2. Now, we just argued before, and there is a D that certifies it, that Q1 and Q2 are distinguishable. And therefore, we can conclude that Q0 and Q1 are also distinguishable because they reached on 0 two distinguishable states. Finally, there is one more location to look. We need to compare Q2 to Q0, and it is also distinguishable, for example, by the string, the symbol 1. So here we saw that every pair is distinguishable, and we can also see that every state is reachable, and we therefore are not going to make any change. So this is, in fact, a minimal DFA. It's a DFA that you cannot reduce. At least our algorithm is not going to reduce it, and we are going to argue that that's good enough. Let's look at another example. So again, Q1 and Q2 are accept states, Q0 and Q3 are reject states. Therefore, this pair is distinguishable from the other pair. We can fill these Ds. And now we have two pairs two pairs to ask if they are distinguishable or not. So let's look at these pairs. How about Q1 and Q2? Q1 and Q2 on 0 stay, both of them stay in Q1 and Q2, both of them stay except, and on 1, both of them go to Q0 and Q3, which so far we didn't determine as distinguishable. So now we're going to move to the other pair, Q0 and Q3. On zeros, both of them reach Q1 and Q2, which are so far we didn't determine to be distinguishable. And on 1, they stay put at Q0 and Q3. They switch roles. And again, we didn't discover that these are distinguishable so far. So now with U, I just completed an iteration where I went over every empty square and every possible symbol, and I didn't find an evidence of two states that are distinguishable, and therefore I will conclude that the remaining spaces are indistinguishable. I didn't prove that it is correct to do, but that's what I want to do. So what are the properties of this algorithm? First, there is a property of efficiency. This algorithm is polynomial time. The reason is that at each iteration, I'm going to either stop or to fill up another square in the table. The number of squares is at most the number of states squared. And so the number of iterations can be at most that. And in each iteration, I go over every pair of states and every symbol. So all of this is polynomial in the number of states and in the alphabet size. So the algorithm that we have is efficient, but the real question is it correct? So the claim is that if P and Q are marked distinguishable by the table filling algorithm, then P is distinguishable from Q. And this is the easier side because that's how we constructed it. So by induction on the number of steps in the algorithm before we marked PQ as D, we are going to argue that whatever we mark in D represent states that are distinguishable. So if PQ are marked D at the start, then it means that one of them is an accept state and one of them is a reject state. Therefore, these Ds that we just do in the first step are justified. They are representing distinguishable states. States that are distinguished by epsilon, by the empty string. So we have the base case. Now we want to prove the induction hypothesis. So suppose PQ is marked D at a later point, then what we know is that, so the way we marked it, or the reason we marked it, is because there are P prime and Q prime that made us mark it. So there is P prime and Q prime that have the properties that they were already marked D before, and therefore by induction, P prime is distinguishable from Q prime, right? We said that for whatever happened before is correct. And for some symbol sigma, we have that P prime is the state you get from P on sigma, and Q prime is the state you reach from Q on sigma. And we want to take these two things together to argue that P and Q are indeed distinguishable. And I already hinted about this before. So we're going to concatenate sigma to the evidence we had before. So P prime and Q prime are distinguishable, therefore by definition there is W that distinguishes them. So W is such that without loss of generality, when you start with P prime and read W, you're accepting, and when you start with Q prime and read W, you are rejecting. Therefore, the string sigma W is going to distinguish between P and Q. Because when you read sigma W from P, you reach the same state as when you read when you read just W from P prime, and similarly with Q prime. So you're going to accept from P on sigma W and reject from Q on sigma W. That's the easier side. That's why we did it. So whenever we are marking something as distinguishable, then it is justified. We have evidence, we have reason to do that. The more challenging thing is to say that if we didn't mark it, then things are actually indistinguishable. So that's a little bit harder. So if PQ is not marked by D, then they are actually equivalent. And if this claim is true, then the table filling algorithm is correct. And it's also efficient, so it does what we want. So the proof is going to be by contradiction. Let's assume that there is a pair PQ that is not marked D by the algorithm, yet P is actually distinguishable from Q. So this is a pair that we want our algorithm to discover and to put a D in the right cell of the table. And we call this pair a bad pair. This is a pair on which the algorithm failed. So this is a bad pair. So we assume that there exists such a bad pair. And every bad pair has a string W, a non-empty string W, such that without loss of generality, when you read W from P, you accept, and you read W from Q, you reject. Why can we assume that W is non-empty? Think about it for a second. Well, if the empty string distinguished P from Q, it means that one of these states is accept, the other one is reject, and this is something our algorithm does know to recognize. So we can assume that there is a non-empty string that distinguishes them. Okay. So we assume that there is a bad pair. There may be many bad pairs. And each one of these bad pairs have potentially many strings that distinguishes them. So we want to define PQ to be not only a bad pair, but a bad pair with the shortest distinguishing string W. So for any other bad pair, including for P and Q, there is no W that's shorter, no W prime that's shorter than W that is that distinguishes this P prime and Q prime. This is the shortest distinguishing string, and this is important. This is how we're going to reach the contradiction. So W is non-empty, so we can rewrite it as sigma W prime for some string W prime. W prime can be empty. And for some sigma, which is an alphabet symbol. And now I want to look, so P and Q are bad pairs. I want to look at P prime and Q prime, which is the states you reach from P and Q on sigma. There are two options. Either one option is that these two states have been marked by our algorithm as D, distinguishable. But that's impossible, because if that happened, then we would also mark PQ with D, right? Our algorithm only stops after, when you look at every pair, like PQ that is not determined, and any symbol sigma, you don't reach a distinguishable pair. So this means that P prime and Q prime are also a bad pair, right? This is a pair that is distinguished by W prime, and it's a pair that is not marked by our algorithm in D. This means W prime distinguishes P prime from Q prime, and it's a contradiction to our assumption that PQ is the bad pair with the shortest distinguishing string. So we found here P prime and Q prime that are also a bad pair and have a shorter distinguishing string, W prime. W prime is shorter by one symbol than W. So that's our contradiction. Let me stay a little bit longer here and say that there is something interesting going on here. Right, we know that two strings are distinguishable if there is a string that distinguishes them. So two states are distinguishable if there is a string that distinguishes them. But there is no limit on the length of the string. And in this algorithm, we are uncovering distinguishing strings that are always larger by at most one than the previous distinguishing string. So this entire algorithm as a byproduct also gives us a bound on the length of a of the minimal distinguishing string. So for two states, P and Q, that are distinguishable, we actually know that their shortest distinguishing string cannot be too long. It cannot be longer than the number of iterations that we have for this algorithm, which is less than Q squared, the number of states squared. In fact, there is a way to argue this directly by a method that's similar to the pumping lemma, the way we prove the pumping lemma. So feel free to think about it, and if you want, you can ask me in one of our meetings. So we have an algorithm for finding the equivalence classes, and now we can define the algorithm that outputs a mean that is supposed to be the minimal state DFA, which is equivalent to M. So that's the algorithm we said before that we're going to have. The algorithm itself is going to be simple now with what we have in our disposal, and it's going to be exactly the thing I've been hinting repeatedly on. So what are we going to do? First thing is going to remove all inaccessible states from M. There's no point in having an inaccessible state. It never is reached, so it never takes part in the calculation of the DFA. Then we run the table filling algorithm on M to get the equivalent classes. And these equivalent classes are going to be the states of the new automata. So we're going to define M mean by the family of states Q mean, the same alphabet sigma, transition delta mean, Q0 mean is the start state, and F mean is the final state. And all of these are going to be defined exactly in the way we expect them to. So Q min is just the equivalent classes of M, as we said. Q0 min, the start state, is the equivalent class of the original start state. F min is the equivalent class of every accept state. So for every accept state, we look at the equivalent class that corresponds to this accept state. All of these are going to be accept states in M min. And delta min, the transition function, takes as input a state, which is an equivalent class. So let's say the equivalent class for Q, and a symbol sigma. And it looks at what the original DFA, what M does on Q, which state that it gets when it starts at Q and read sigma. And it takes the equivalent class of this state. So if from Q on sigma you reach Q prime, then you output the equivalent, you reach the equivalent class for Q prime. Essentially, all of this is a very complicated way of saying exactly what we wanted before. We take equivalent classes and we merge all the states in every equivalent class. And the claim is that these accept the same language. And this is based on just the definition of these equivalent classes and the correctness of the table filling algorithm. And I will not get into the details. You can prove it by induction. But essentially, the first step of removing all inaccessible states gave us the same, an equivalent DFA. And now the next step of merging all the states in an equivalent class preserve the language, because states in an equivalent class are indeed equivalent. You can forget where you are within the equivalent class. So let's look at an example of this algorithm. We have these three states, Q0, Q1, Q2, and we are going to reach these two states. And essentially, the reason is that Q0 and Q1 are equivalent. So the table filling algorithm would show us that naturally Q0 and Q2 are distinguishable, Q1 and Q2 are distinguishable, but Q0 and Q1 are indistinguishable. Let's look at a more complicated example. What's the first thing we're going to do for this finite automata? Let you think for a second. The first thing is to remove inaccessible states, and here we do have one inaccessible state, Q2. We can get rid of it. Now we're going to run the table filling algorithm. We know that Q5 is distinguishable from everything else. And now, one by one, we are going to identify other distinguishable states. So we can show that Q1 is distinguishable from Q3 and Q4. Both of them, when you take a 1 from Q1, you reach Q0, whereas when you take a 1 from Q4 or Q3, you reach Q5. And Q0 are distinguishable from Q5, and therefore we have these distinguishing values. Similarly, we can show that Q0 is distinguishable from Q4 and Q3 because when you take a 0 from Q0, you reach Q1, and when you take a 0 from Q4, you reach Q4. Similarly, from Q3, you reach Q4. We already know that Q1 and Q4 are distinguishable, and therefore we can conclude that Q0 and Q4 and Q0 and Q3, both of them are distinguishable. So we are left with two questions. Is Q1 distinguishable from Q0? And if Q4 is distinguishable from Q3? So let's take the first one, Q0 and Q1. What do you think? Well, 1 will not distinguish them. 1 will reach Q0, but 0 from Q0 reaches Q1, and 0 from Q1 reaches Q3. And we already argued that Q1 and Q3 are distinguishable, therefore Q0 and Q1 are distinguishable. We're left with Q3 and Q4, and you can verify that they are indistinguishable, meaning that when we look at just one symbol, it won't distinguish them, and because of the proof we already have, this is enough. So Q3 and Q4, if you take a 0, you reach Q4. If you take a 1 from both of them, you reach Q5. There is no way of distinguishing them. And so we know that there is most vertices are equivalent classes on their own, but Q4 and Q3 are an equivalent class together, and we can merge them. And this gives us the automata that is minimal. So what have we done so far, and what's left for us to do? What we've shown so far is that this algorithm that we have gives us another automata that is equivalent to the one we started from. And also we know by definition that this mean, the automata that we are producing, is irreducible. There are no more equivalent states there, and all the states are accessible. So these are the properties we have. The question is, are these properties sufficient? Do we get something that's minimal? And then do we get something that is uniquely minimal? And the interesting thing is that if that's correct, if what we get is minimal, it means that by doing these simple ways of reducing states, either by removing inaccessible states or combining states that are indistinguishable, these are ways to reduce the size of an automata. But who said that these kind of local changes are the only way? Perhaps there is something global that can be done that's much smarter and can reduce much more. So this would tell us no. Once you do these two things, you remove inaccessible states and combine equivalent states, then you're done. So let's look at the theorem that we have. The theorem is that M min is the unique minimal DFA that is equivalent to M. And to prove it, we'll prove the following claim. The claim is that if L of M prime, so some other automata M prime, is the same as L of M min, and M prime has these properties that we like, it doesn't have inaccessible states, and it is irreducible, then there is an isomorphism between M prime and M min, meaning that M prime and M min are essentially the same automata up to renaming. Isomorphism is something that we'll formalize soon, but essentially it's just a mapping of names. You're replacing the name of states, and you can move from one to the other. So I want to say that this claim is enough to prove the theorem. So, and then we will be left with the challenge of proving the claim. This will be a more complicated proof. The claim is not obvious. because we need to verify, we need to create this isomorphism, and we need to prove all the properties of isomorphism. But the part that is easy is that from the claim, we can prove the theorem. And this theorem completes what we wanted, completes the idea that we have an algorithm that minimizes DFA and gives us the unique DFA. So assume that the claim is true. Then define M prime to be a minimal DFA for the same language. A minimal DFA certainly satisfies the condition of the claim. A minimal DFA has no inaccessible states and is irreducible. Otherwise, we can get an even smaller DFA by removing inaccessible states or combining states. So M prime satisfies the condition of the claim, which means that M prime so that there is, because M prime satisfies the condition of the claim, there is an isomorphism between M prime and M min, which is the output of our algorithm. So it means that the output of our algorithm is indeed the same as the minimal DFA, as any minimal DFA. So since this M min is identical, is equivalent up to renaming to any minimal DFA, it means that it is the unique DFA up to renaming. So the theorem holds. Okay. So believing the theorem, we finished everything, but to believe the theorem, we need to believe the claim. And that's one last part of this proof. I do kind of agree that this is a long proof. It's almost pushing the kind of the boundaries of what you can prove with slides and in a video. So this is a great place to take a short break, exercise a bit, and get the blood flowing. I would do it too if I didn't want this to be a single video. So I'm continuing, but you can pause and do something fun. Ooh. So now we want to prove the claim. So to prove the claim, we want to recursively construct a map from the state of M min to the states of M prime, and this map should satisfy all the conditions of an isomorphism. So let's define the mapping, and later we'll remind ourselves what are the conditions of isomorphism that we need to prove. So the base case is just that a start vertex is mapped to a start vertex. So the start vertex of M min, Q0 min, is mapped to Q0 prime, the start vertex of M prime. And now a recursive state. If P is mapped to P prime, and for some symbol sigma, P transitions to Q in M min, and P prime transitions to Q prime in M prime, then we are going to map Q to Q prime. This is a recursive way of creating a mapping. So far, I'm saying nothing, I've proved nothing about the properties of this mapping. Actually, I didn't even prove that it is a mapping, that it is well defined, for example. All of this is ahead of us. But this is the definition. And we need to prove that it is a mapping and that this map is actually an isomorphism. So what are the properties we need to prove? First, that this mapping is defined everywhere. So for every P, there is a P prime that P is mapped to. We need to show that the map is well defined, meaning that P cannot be mapped to two different states, P prime and Q prime, that are different. The map is bijection, and the map preserves all transitions. So everything is great, but I can always map, kind of have a one-to-one mapping from the state of one automata to the state of another, if I'm not required that this mapping is going to satisfy the condition of the transition, kind of transition function. So if P is mapped to P prime, then delta of M mean of PQ is mapped to delta prime of P prime sigma. Now, this part we are getting for free. We're getting it just by construction. Because if because of the way we define the mapping recursively, if P reaches Q on sigma and P prime reaches Q prime, then we are going to define Q is mapped to Q prime. So if this holds, if P is mapped to P prime, then our algorithm is going to define the mapping that is required. So the delta mean of P sigma is mapped to delta prime of P prime sigma. So what we need to prove, so this part is easy. We need to prove that the map is defined everywhere, that it is well defined, and it is a bijection. It is one-to-one and onto. Essentially, it is kind of renaming of the states. So let's try to prove these four properties, and then even I will deserve a break. So the map is defined everywhere. It means that for every state Q in a mean, there is some Q prime that you are mapped to. If we are not mapping some Q, then it's not a mapping. So if Q is in a mean, then there is some W such that from Q0 mean on W reach Q. So why is this correct? Well, we assume that there are no inaccessible states in M mean. We constructed it such that there is no inaccessible state in M mean. And therefore, there is a path from the start vertex to Q. And we'll take W to be a word that leads you down this path. Now let's define Q prime, which is the state you reach in M prime from the start state Q0 prime when you read W. And a claim that's not very hard to show is that Q is going to be mapped to Q prime. And this can be shown by induction. So we know that to begin with, Q0 mean is mapped to Q0 prime. And then we take the first symbol of W and we see which states we reach. We know that we are going to map one to the other. And we can continue all the way to the final state we reach, which are these Q and Q prime. And we know that Q is going to be mapped to Q prime. So this is not hard and can be proved by induction, and I'll leave it to you. The map is well defined. This is more challenging. So what does it mean? It means that for every states Q prime and Q double prime that are distinct, we shouldn't have that Q is mapped to Q prime and Q is also mapped to Q double prime. And recall that we didn't check consistency. We defined these things recursively, and we may reach the same vertex several times, and perhaps every time we reach it, we are going to map it to some other state. So this is not obvious. We need to prove it. We'll prove it by contradiction. Suppose that there are states Q prime and Q double prime, such that Q is mapped to Q prime and Q is also mapped to Q double prime. We are going to show that Q prime and Q double prime are indistinguishable. And since Q prime and Q double prime are indistinguishable, they have to be the same. Why do they have to be the same? They have to be the same because in M prime, we know that M prime is irreducible. There are no indistinguishable states that are different. So again, we assume that Q is mapped to Q prime and to Q double prime, and we need to show that Q prime and Q double prime are indistinguishable, and that's enough for us. Let's prove that. Let's look in these parallel worlds, what happens in M mean and what happens in M prime. And we assume again, for the sake of contradiction, that Q prime and Q double prime are distinguishable. So first, we know that Q prime is reachable by some U, and Q double prime is reachable by some other word V. And we're going to take these U and V to be exactly these two strings that caused us to map Q to Q prime and caused us also to map Q to Q double prime. So if we mapped Q to Q prime, then we mapped it recursively. And we can trace our way back and find a sequence U that made us essentially map Q to Q prime. And similarly, V that made us map Q to Q double prime. Right? The way we map states to each other is by this recursive operation that always starts with the fact that we mapped Q0 mean to Q0 prime. So that's just a property of our algorithm. So far, everything on the slide just follows from the fact that Q is mapped to Q prime and Q is also mapped to Q double prime. Now let's take the assumption that Q prime and Q double prime are distinguishable. This means that there is some W such that you reach from Q prime on W to accept and Q double prime on W to reject. Now let's remember that M mean and M prime are equivalent. They accept the same language. What does it mean? It means that U W also reach accepts on M mean and VW also reach reject on M mean. But now we reached something that's absurd. It's a contradiction. We reached two contradicting conclusions. We reached the conclusion that from Q on W you reach accept, and from Q on W you from Q on W you reach accept, and from Q on W you also reach reject. This is a DFA. From Q on W you either accept or reject. You don't do both. So this is a contradiction. That's a little bit tricky. Perhaps you need to rewind me a couple of times or ask me questions in our meeting. Okay, so we have a contradiction and we have a few more properties to get through. So we want to say that it is a bijection. So one thing is to show that it is onto. So So we want to show that for every q prime in M prime, there is something in M min that is mapped to it. So q is, there is some q that q is mapped to q prime. For every q prime, there is a string w, so that M prime reaches q prime after reading w. Why is this correct? This is correct because in MW there are no unreachable states. So in particular, q prime is not unreachable, and there is some w that would reach it. Now let's look at q, which is the state M min reaches after reading w. And now, recursively, like we had to do several times before in this proof, we can show that q is mapped to q prime. If you trace our algorithm through w, starting from the start vertex, you'll reach the idea that q is mapped to q prime. The algorithm will map q to q prime. So this is similar to things we already argued before. And potentially this is the last thing we need to prove. If I'm not forgetting, we'll see in a second, that the map is one-to-one. This is going to be tricky in a similar way to what we already proved before. The proof is by contradiction. Suppose that there are two distinct states, P and Q, such that P reaches Q prime, and Q also reaches Q prime. Is also mapped to, sorry. P is mapped to Q prime, and Q is also mapped to Q prime. Let's assume that something like this happens. It means that the mapping is not one-to-one. We want it to be one-to-one, and onto, if nothing else, in order to claim that the number of states in these two finite state machines is the same. So we definitely want these properties. And let's again look at the parallel worlds, one in M min and one in M prime. What happens there? Now let's again look at U that reaches in M min P and V that reaches in M min Q from the start vertex. And let them be the U and V that made us map P to Q prime and made us map Q to Q prime. So when you read U from Q0 prime, you reach Q prime, and from Q0 prime, when you reach V, you read V, you reach Q prime. Now we want to use the fact that P is different than Q. And if P is different than Q, they are also distinguishable. And if they are distinguishable, right, why are they distinguishable? Our algorithm outputs something that is irreducible. Then there is a W that's going to accept from P and reject from Q. But M min and M prime are equivalent. They accept the same languages. Therefore, when you read UW in M prime, you accept. When you read VW in M prime, you reject. And again, you reach a contradiction, because it cannot be that from Q prime you both accept on W, and from Q prime you also reject on W. So that's a contradiction. So this was a very long and long proof. I hope that with the aid of this video, by asking me additional questions when we meet, and with the notes, you can make sense of everything I said here. But taking this into account, taking what we learned here into account, the fact that you can minimize DFA, then how can we prove, I can ask you a question, how can we prove the two regular expressions are equivalent? And I really suggest that you pause me here and try to answer it yourself. So assume you're back, and the way is pretty easy. We use the fact that from a regular expression, we can construct a DFA. So these two regular expressions will give us two DFAs. Now we're going to minimize each one of them, and we're going to check if they are equivalent. And know that everything that we did today is constructive. So the algorithm that, well, and everything we did before. So the regular expression to DFA is a constructive thing. So actually regular expression to an NFA, and then you can turn it into a DFA. Then you can minimize. And now remember that checking if these two are have an isomorphism, the construction of the isomorphism was constructive. So we can start constructing this isomorphism and see if it works, if the construction works. So before we conclude, let's meditate on what we've seen. So what we've seen is that DFAs can be optimized in a very, very strong and powerful way. And what we're going to do in 2 videos is ask, can DFA be learned? So this is going to be a task that's a little bit harder. And essentially it says if based on partial specification, we can come up with a DFA. This will be a taste into learning theory. We won't get into it very deeply, but it will be a taste of that. Thank you.